Central limit theorem is an extension of the normal distribution problems that we did from the last unit. Basically, it asks the question, what happens if we take a sample size greater than 1? So all the normal distribution questions we answered previously were phrased, what's the probability that an individual, that one randomly selected person? For the normal distribution, we can do that, but now say, what's the probability that 30 randomly selected people have an average above a certain number, below a certain number? So basically, we're going to look at sampling means and standard deviations of sample sizes greater than 1. What the central limit theorem tells us is for any given population with mean, mu, and standard deviation sigma, the sampling distribution of sample means will have the following 3 characteristics. If either the sample size n is at least 30 or the population is normally distributed. So these words here, at least 30, I'll warn you, some books have different numbers there. I've seen it as 25, I've seen it as 40, I've seen it as 50. I think 30 is a reasonable number for this. Basically what you're going to see is if you take repeated distributions from any type of distribution, so repeated samples I should say, slowly it becomes a normal distribution. So the one that I like to do on the board a lot is one that uses dice, where basically if I roll a die one time, the distribution looks like a uniform distribution. 1 is as likely as 2, is as likely as 3, 4, 5, 6. If I roll a dice 2 times and take the average, it turns out that getting an average of 1 is much harder. You'd have to roll 1 both times than, for instance, getting an average of 3.5. Because the 3.5 comes from rolling a 7, which you could get as 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, or 6, 1. What I'm trying to say is you would see that over time, any distribution slowly piles up in the middle is most likely and gets longer tails that are less likely. Where it actually becomes exactly normal is up for dispute. So when I talk about that magic number 30 for your class, we're basically saying that once you take 30 observations, it's close enough to a normal distribution that we can use the numbers that have been calculated in the normal distribution. You'd still rather have a larger sample size, it would make it more closely fit the table, but basically once we hit 30 observations, it doesn't matter if it was normal to begin with, we now say we can use the normal table. As long as we use the mean based on what the original mean of the underlying population was. So this is the easiest math you'll do. Basically, if you're given a mean, rewrite it, that's the new mean of the sample. Slightly more difficult is finding the standard deviation of the sample. Basically, you take the given standard deviation of the population and divide by the root of n, or how large the sample is going to be. So to find the standard deviation of the sample, it's what the original standard deviation was divided by the root of n. The shape of a sampling distribution of sample means will always approach a normal distribution regardless of the shape of the original distribution. The bigger our samples are, the closer it will approximate. So again, 30 is our magic number. As long as we have 30, we're going to use the table and say it's a good fit. But the more samples we have, the larger samples we have, the more it'll be a normal distribution. There's literally no calculation here when we find the mean of a sampling distribution. If I tell you the mean of a distribution is 7, what's the mean of its sampling distribution? Answer is 7. It's not a trick. Mean of the sampling distribution is the same as the mean. As opposed to when we have to calculate sigma sub x bar, it's sigma over root n. If the original standard deviation was 3, what's the standard deviation if you're taking samples of size 81? So this would put 3 where I see sigma. Where I see n, I'd put in 81. So it would be 3 over the root of 81. That would become 3 over 9, or 1/3. So here's the math. I plug in sigma that was given here as the standard deviation on top. I plug in n as the size of the sample that we're going to take on bottom. And then I reduce. Both together, find the mean of the standard and the standard deviation of the sampling distribution of sample means using the given information. So right off the bat, if I want to find mean mu sub x bar, for the first one, it's 10. How do I know? Because the original given mean was 10. I'm just repeating back what the given mean was. When I go to find the new sigma, here it would be 2 divided by the root of 64, which is 2 over 8, or 1/4. For number 2, again, I'd repeat the mean. Since the mean is 3, the mean of the sampling distribution is 3. Then 1 over the root of 100 is 1 over 10, or 0.1. 0.2 is the mean of this. 0.7 divided by the root of 49, or 0.7 divided by 7, also gives me 0.1 for sigma sub x bar for this. For number 4, the mean I just report is negative 80. 30 divided by the root of 225 is really 30 divided by 15, so this would give me 2 as my sigma sub x bar. For number 5, I'd repeat back the mean is 50. I'd then take 5 divided by the root of 400. Root of 400 is 20, so 5 divided by 20 is 1/4, or 0.25. So we can see these done out. Every time the mean is just repeated back as the mean of x bar. And then I talked out how to do each of these calculations, but again, basically to get these numbers on the right-hand side, all I'm doing is taking the given sigma divided by the root of n. The study of PA college students found that they spend an average of 15 hours a week studying with a standard deviation of 3 hours. If 144 are going to be sampled, what are the mean and standard deviation of the sampling distribution? In this case, since we know that the standard deviation, let's start with the mean. Since we know that they spend an average of 15 hours a week studying, the mean of the sampling distribution would also be 15. I would then want to take the standard deviation 3 divided by the root of n, which in this case is 144. 3 over the root of 144 turns into 3 over 12, or 0.25. For the second one, they tell us that the pharmaceutical companies create an average of 40 pounds of pollution a day with a standard deviation of 10 pounds. So where we're going to start, this 40 is going to be the mean of the sampling distribution. Then, if the group is going to look at a sample of 100 companies, the standard deviation is going to be the 10 pounds that was the standard deviation, divided by the root of n, which in this case is the root of 100. 10 over root of 100 is 10 over 10, or just 1. For the standard deviation of the sampling distribution too. So there we can see we have mean 15, standard deviation 0.25, mean 40, standard deviation 1. According to the central limit theorem, if either the sample size n is at least 30 or the population is known to be normally distributed, then the standard score for a sample mean and sampling distribution is given by. It's basically the same exact formula as what we had before. We're changing in the z-score formula. Instead of writing just x, it's x bar, because really we're taking a number of different observations and then taking the mean of those observations. So x bar is a sample mean that we're given, and we're trying to find what's the probability that the sample mean is above or below this number, or between these two numbers. This mu sub x is the same. Sigma sub x bar on bottom, again, we're just replacing by sigma over root of n. Most of the time I do that sigma over root n within the larger calculation, but there also could be times where you want to do it separately. Just make sure when you're then dividing by it that you don't round it too much, because even the slightest little bit of rounding does significantly change what z you would come up with. So, calculate the z-score in the given situation. Calculate the z-score for 1, we're going to take 28, subtract 30, that's going to give me -2. I'm going to divide by 6 over the root of 50. Can't do root of 50 in my head, but I promise it'll be showing up here. In number 2, we're going to do 1234 minus 1200, divided by 100 over the root of 100, which is 100 over 10, or 10. So 1234 minus 1200 would give me 34 divided by 10 would give me 3.4 for this z-score. For problem number 3, I'm going to take negative 4.95 minus a negative 5, which will give me positive 0.05, divided by 1 over root 44, which again I can't do in my head. Here is the math correctly done out though. So for the first one, we get -2 on top, 0.849 on bottom. which gives me a z-score of negative 2.36. For the second one, we get a z-score of 3.40, and for the third one, we get a z-score of 0.33. Notice each time that the key distinction is this bottom part where we're doing the standard deviation divided by the root of n. I would put parentheses around everything as you're putting it in to make sure that everything is going in the right order. Suppose the average number of times a recent high school graduate has been to the hospital is 5, with a standard deviation of 2.4. A sample of 36 recent high school graduates is taken. What's the probability an individual student has been to the hospital less than 4 times? What's the probability the mean of the sample taken is less than 4 times? So this is asking 2 different probability questions. The first one's like what we could have done in the last unit. The next one is particular to using the central limit theorem. So when I just answer the question about an individual student being to the hospital less than 4 times, basically I say, well, since the mean is 5, my x value is 4, I do 4 minus 5, and then I'm going to divide it by the standard deviation of 2.4. After I do that division, it will give me a z-score. I get out my table, I look up the z-score in the table, and that tells me less than. I do the same calculation down here when I do it for the mean of the sample. The only difference is, instead of dividing by 2.4, we'll be dividing by 2.4 over the root of 36, or really, we'll be dividing by 0.4. So what that means is we're going to have a much larger z-score, or in this case, since it's negative, we'll have a smaller z-score, more negative, further from the mean, when we do it for just one individual, as opposed to when we do it for the mean of the sample. So here we can see z 4 minus 5 over 2.4 gives me negative 1 over 2.4, which has a z-score of negative 0.42, a p-value of 0.3372. As opposed to when we do it for the mean of a sample, when we're taking 36 observations, then it becomes negative 1 over 0.4, which is negative 2.50, and has p-value 0.0062. So in real world terms, what this means is, if we're only looking at one student, the chance that they really haven't had anything serious happen and they've been to the hospital less than 4 times is 33%. So somewhat likely, almost 34% really. As opposed to if we take 36 students, and it's true that on average somebody of that age has been to the hospital 5 times, the chance of us finding 36 people who are all less than the average and unlikely to go to the hospital, it's not as likely to happen. From 33% for just one person being able to fit in there, to 36 people being less than 1% chance. So what's really happening here is because the standard deviation is smaller, that raw distance that I am from the mean, which was 1 in either case, gets magnified when I'm taking the sample, as opposed to when I'm just saying what's the probability of a random one person having this value. Suppose the average number of times a recent high school graduate has been to the hospital is 5 with standard deviation 2.4. A sample of 36 recent high school graduates is taken. What's the probability the mean of the sample is more than 4.5 times? So again, the key difference here is we're going to be dividing by 2.4 over the root of 36. Otherwise, we'd use the same methods. For more than, we're going to find the z-score, look for the associated p-value, and do 1 minus that p-value to find the probability indicator. So we're going to take the 4.5, that's the given x bar value, subtract the given mean of 5, divide it by the given standard deviation of 2.4 over the given sample size under the square root. So it becomes negative 0.5 over 0.4, which is negative 1.25 as a z-score. That z-score points me to 0.1056, which really says the probability of getting less than 4.5 times as the mean of my sample is 10.56%. Since we want more than 4.5 times, we do 1 minus that 0.1056 to wind up with 0.8944, or 89.44% of the time. Our sample of 36 students would have gone to the hospital on average more than 4.5 times. Same prompt, what's the probability that we're between 4 and 4.5? So the good news is, just like before, when we've already found z-scores, we can use the previous z-scores that we found. So in the two previous questions, we found a z-score for 4 and a z-score for 4.5. We use those two probabilities taken by saying larger p-value minus smaller p-value is between. So previously we found negative 2.50 at p-value 0.0062 and negative 1.25 at p-value 0.1056. So we do the larger minus the smaller, 0.1056 minus 0.0062, and find 0.0994, or in other words, right around a 10% chance that the mean of our sample is between 4 and 4.5. Suppose the mean amount of money a college student has on them is $35 with a standard deviation of $12. A sample of 80 college students is taken. Find the probability that one student has less than $38 on them. Find the probability that the mean of the sample taken is less than 38. Find the probability the mean of the sample is more than 36. Find the probability that the sample mean is between 36 and 38. And then find the probability the sample mean differs from the population mean by more than $1. So a lot to take in here. Basically, the first one is just a regular z-score where we're not going to divide by the root of 80 for the standard deviation. We're just going to do 38 minus 35 over 12. Part B is the same thing, except we're now going to divide by the root of 80 when we look at the bottom of that z-score formula. For part C, we're going to use 36 instead of 38, and we're going to do 1 minus the probability we find after finding the z-score and p-value because it says more than. For part D, we're going to use the two z-scores we found above, larger p-value minus smaller, to find between. And then really, when we say what's the probability this sample mean differs from the population mean by more than $1, what we need to do is find the probability between being $1 less and $1 more than the mean, and say 1 minus that between is the probability that you're outside and that you do more than $1. So here's everything being worked out. It looks like we can't really see the bottom here, so I might have to go back to the bottom. But basically in A, since it's one student, it's just 38 minus 35 over 12, which gives me a z-score of 0.25 and points me to a p-value of 0.5987. For part B, when we do 38 minus 35, but instead of just dividing by 12, we divide by 12 over the root of 80, it makes it a much larger z-score with a larger p-value. So the probability that the mean of the sample is less than $38 when we're looking at 80 students becomes 98.75%. For part C, the probability that the mean of the sample is more than $36, we do everything to find the z-score that we did above, but once we find this p-value in the table by looking up 0.75 on the positive side of the table, we have to do 1 minus the p-value to find the answer to our probability question. So we get 0.2266. When we're asked find the probability the sample mean is between $36 and $38, we take the larger p-value, 0.9875, minus the smaller p-value, 0.7734. Remember, we're using the table values that we found, not the change table values by doing 1 minus to find the more than. We're looking at the original two p-values, larger minus smaller for in between.